Okay, right. Today we're going to learn about finding the nth root of a complex number. Let me give you an example. Let's say we want to find the fifth root of minus 32. We want to find the answer to that. Now, I know minus 32 doesn't seem like a complex number, but it can always be plotted on the complex plane. If I was to draw the complex plane here, that's the imaginary axis, that's the real axis, and minus 32 is going to end up somewhere over here. Okay. And let's say we want to find the fifth root of that. You can see immediately that one of the roots is going to be minus 2 down here. We've got to find the other ones. There's 5 of them, and they're going to be somewhere in the complex plane. They might have an imaginary part as well, and we don't know where they are, so we've got to find them. So, of course, minus 2 times minus 2 times minus 2 times minus 2 times minus 2 is going to give us minus 32, but we can find that one nice and easy. But we're going to have to use something a bit clever to find the other ones. Okay, right, let's say that, let's be more general now, and let's say that our complex number is given by cos alpha plus I sine alpha. And let's say that the nth root of that will be general now. We won't say the fifth root, we'll say the nth root of that is another complex number given by cos theta. Here's a different colour. Given by cos theta plus I sine theta. Well, obviously, cos theta plus I sine theta to the power of n must equal cos alpha plus I sine alpha. Right, if we use de Moivre's theorem, I'll see if I can get that right, de Moivre's theorem, we'll get cos n theta plus I sine n theta equals cos alpha plus I sine alpha. If you don't know how I've got from here down to here, that's simply using de Moivre's theorem. I pronounce it differently each time. Why not? That's using de Moivre's theorem. If you don't know about that, just look it up in your textbook. Basically, it's just, it can easily be proved, and it's just a straightforward equality that if you've got cos theta plus I sine theta to the power of n, that's equivalent to cos n theta plus I sine n theta. Well, now that we know that this is equivalent to this, we can see an immediate relationship between theta and alpha, namely that n theta equals alpha. Well, I'll modify that a bit because n theta equals alpha plus 2k pi. Why do I say plus 2k pi? Because n theta could, to give us the same result, to end up as, let's say this represents some number in the complex plane, its argument, let's say, just for the sake of our discussion, we'll say the number we're trying to get to is here. Well, and its argument there is alpha. Obviously, n theta, well, we could go around again. We can add 360 plus alpha. We can add 720 plus alpha. So we have the 2k pi here. Now, the reason why the 2k pi is relevant is because we're going to get 5 different answers. Without that 2k pi there, we wouldn't get 5 different answers. So what values does k take on? Well, k can obviously take on any value because we can keep on adding 2 pi as many times as we want. But the only values of k which are relevant to us are 0, so k equals 0, 1, 2, up until n minus 1. Why don't we go above n minus 1? Well, I'll tell you why. Because theta equals alpha over n plus 2k pi over n. Let's say n was equal to 5, as it is in this example here. If n equals 5, you'll get, sorry, that should be plus. Oops, making some mistakes there. Plus. When n equals 5, if we can get different values for this, for theta, putting in k equals 0, 1, 2, 3, 4. But once we put in k equals 5, this would be 2 times 5 pi over n, which is 5. So it would be 2 times 5 pi over 5. In other words, we'd just be adding 2 pi. So we'd come back to the case where theta equals alpha over 5 again. Well, we had that when k equals 0. So in other words, we'll just be repeating ourselves. So as we'd expect, if in the case where n equals 5, k would equal 0, 1, 2, 3, 4, and we'd have 5 roots. We couldn't get any more than that because we'd expect 5 roots of an expression like this, 5 possible answers. Okay, so that's the general solution. Theta equals alpha over n plus 2k pi over n. Well, let's go back to our original question where we said we were going to find the 5 roots, or fifth roots of minus 32. Let's put that in the complex plane and apply this formula and see if we can see if it gives us what we expect. Or let's have a look and see what it gives us. Okay, right, so we'll draw the complex plane. That's the imaginary axis. That's the real axis. And we've got minus 32 somewhere out here. Minus 32. Okay, now we know without even thinking about it that one of the answers is minus 2. One of the roots is minus 2. So we put that one in immediately, minus 2. Now there's another 5, and they're going to be somewhere in this complex plane, having both imaginary parts and real parts, and this formula here will help us find them. And they're all going to have a modulus of minus 2, because when you multiply a complex number by itself 5 times, you multiply the modulus by itself 5 times and add the argument to itself 5 times. So if you're multiplying the modulus by itself 5 times, it will be 2 times 2 times 2 times 2 times 2, which is going to give you 32. So they're all going to lie on a circle of radius 2. So I'll draw that circle in now. I'll draw that in a nice red colour. There we go. All of our roots are going to lie on this circle. We've got one already, that's that one there. So I'll put that one in for you. That's one of the roots in the complex plane. I don't know, I'll label this for you just so as you know that's the imaginary axis and this is the real axis. Okay, right, now let's try using this formula. What does alpha equal? Well, alpha is going to be the argument of the original number we started with, which was minus 32. Well, the argument of that is going to be pi. It's the angle measured from there to there. So we can stick pi straight into there. So theta equals pi, and n equals 5. We wanted to find the fifth root of that, remember? Got to the question up here. want you to find the fifth root of minus 32. So n is 5, so it's pi over 5 plus 2k pi over 5 for k equals 0, 1, 2, 3, 4. Okay, so if we put k equals 0 in here, we're going to get theta equals pi over 5, which is going to be about there. So there's another one of our solutions, pi over 5. I'll pop that one in for you. Right, when k equals 1, we're going to get 3 pi over 5, which is about there. When k equals 2, we're going to get 5 pi over 5, which is this one here. 5 pi over 5 is pi. Okay, when k equals 3, we're going to get 7 pi over 5, which is about there. And when k equals 4, we're going to get 9 pi over 5, which is about there. If we went to k equals 5, we'd get 11 pi over 5, which is back on there again. So it just repeats itself. That's why we only go up to 4. Okay, so we've got 5 roots to minus 32. And let's have a look at this. If you look, these are conjugate pairs. So four of the roots there have conjugate pairs. They have the same real part and the negative of the imaginary part. Okay, so that's something just to note, which you look out for when you're finding the roots of these things. The other thing you'll notice is that the separation between each of these is going to be 2 pi over 5. So if I put in this angle here, this angle here is going to be 2 pi over 5 in black. 2 pi over 5. Same with this angle here. This angle here is going to be 2 pi over 5 as well. 2 pi over 5. This angle here, 2 pi over 5. This angle here, 2 pi over 5, and this angle here, 2 pi over 5. Okay, so those are the things you've got to look out for, and I hope that that explains to you how you find the roots of any number in the complex plane. You don't have to. You could find the roots of 1, a real number, a real positive number somewhere on this axis. You could find the roots of an imaginary number. If alpha would equal 0 if you were finding the roots of a number on the real axis. Alpha would equal pi over 2 if you were finding something on the imaginary axis. If you had a point here, for example, then you'd be finding the roots of a complex number with real and imaginary parts. So if I was going to find the roots of some number here and say it was 45, that would also give us a solution. We could also use exactly the same thing on if we need to find the roots of this complex number here. In this case, alpha would be about 45 degrees in the example I've shown. You just bung it into this equation here, find your roots, and then plot them on the graph, and it'll be clear to you what those roots are. If you were to multiply this complex number by itself 5 times, you'd end up with minus 32. The same with that one, and that one as well, and of course minus 2, which is another solution. Okay, I hope that helps. See you in the next video. Bye bye.